Today we're going to be discussing Lab 3. The purpose of this lab was to apply the loop rule in charge conservation to analyze series resistor circuits, measure real values of current and potential differences using multimeters, and then investigate the time-dependent behavior of an RC current circuit. I made various models of circuits using Circuit Construction Kit through this experiment, and you will see them later on. The key concepts in this lab include Kirchhoff's loop rule, which says the total potential change around a closed circuit is zero, and charge conservation, meaning current is the same at all points in a series circuit. For the RC part, we looked at how a voltage across a capacitor decreases exponentially as it discharges. Now here are the results. The results shown are just the main result of this lab. Throughout this experiment, we came to find many results, but this is the main one that you will see. As you can see, this is the time dependent of the RC circuit. We have the the voltage change throughout time on a graph, and then we had the slope, which was the constant, and we took the inverse, which gave us 5.47, but the actual results were 6 seconds. For this experiment, I built a circuit with two batteries, which were 1.5 volts each, and then two ammeters, and then two resistors. I was then asked to show the readings on the ammeters, and then to see how they both were the same. And then they are the same because the same amount of charge flows through both of them. If the ammeters are flipped, then the results are the same, but the signs are opposite. Here I took one away, and then ammeters, and then measured the voltage of the circuit. As you can see, the potential difference was 3 volts. Here I took away, the other experiment wanted us to measure just one of the spots, while this asked us to measure the entire circuit. The results of each position were as shown. From A to B were 3 volts, from B to C was 0, from C to D was 0.96, from D to E was 0, E to F is 2.04, from F to G is 0, G to H is 0, and then H to A was 0. We then had to put that onto a graph, which is shown, and then we used the equation below to prove that these were the correct values because we found the resistors of each spot, the resistivity of each spot. We were then asked to put an ammeter in a parallel with our resistor and see how the results changed. And as you can see, the results did change because now it was 0.06 instead of 0.02. This is the last part of the experiment, where we were asked to make a circuit with a light bulb, battery, and capacitor. Once the battery gave power to the circuit, the light bulb lit up but once it fully powered, it started to become dimmer, and the capacitor charged up. When the battery was removed, the capacitor discharged through the light bulb. I then took the change in potential difference at 5-second intervals, and this was plotted onto the graph that you saw before. And then I got the slope, and the inverse of the slope was the time-dependent constant. Now, the system for each experiment was the batteries, capacitors, or resistors that were used throughout the experiment, and the surroundings is the environment that the circuit is in. The first part of the what-if question asked us, if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistors in the circuit, how quickly would our ideal model predict the capacitors to reach full charge? Would this prediction happen in real life? Well, a real ammeter has a small resistance, so inserting it into a real circuit would slightly reduce the current compared to an ideal situation. This could lead to a minor difference in voltage and current measurements, especially in a low-resistance circuit. The other what-if question asks us, what if we were doing this experiment in real life and used a real battery to charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach fully charged? The answer to this is that our ideal model predicts that without a resistor, a capacitor charges instantly, since RC equals 0. But in real life, no circuit is resistance-free. Connecting a capacitor directly to a real battery would result in a dangerous surge of current, potentially damaging the components. So while the model is mathematically correct, it doesn't reflect the real-life limitations of resistance and safety. Now, why we perform this lab? We performed this experiment to apply the principles of charge and energy conservation to real electric circuits. In the series circuits, we confirmed that the current stays the same throughout, and the voltage drops across resistors adds up to the total battery voltage. In the RC circuit, we observed how capacitor charges, and discharges over time and uses voltage measurements to calculate the RC time constant. This experiment helped us connect theoretical circuit laws to actual measurements and behaviors. And in this experiment, there were no errors due to it being an online experiment. If it was in real life, there might have been external factors that would change the results of the lab. Thank you.